Right. So the last time we had basically uh, derived the potentials for basically the linear weighted potentials, okay, and we did it by looking at the Green's function solution of in Lorentz gauge. Okay. And so we had the wave equation, we used the Lorentz gauge, it simplified things, and then we used the four-dimensional Green's function to solve, and we found that we can get potentials. There are two solutions, and one of them, the retarded solution, is the physical solution. So we took that, and this was the answer, right? This potential, the phi and the E were given like this. Okay, and so today what we want to do, so and then I have given you a homework problem where you have to basically calculate the electric field and basically the potential, and then of course one can go ahead and do the electric and the magnetic field for a point charge which is moving and accelerating. Okay, that was the homework. Now, going from the potential to the fields is a straightforward thing. It's just clumsy and needs some calculation. So I'm not going to do that. We have done this before, and I decided to omit it. That's just mathematics. If you know phi and A, how to calculate E and B. So you can look up Jackson or any of the books, mainly Jackson, I would say, because some of these notations are closer to Jackson, and find out how to go to the fields from the potentials. We will start from those equations directly and try to see what we can tell about radiation fields. Okay, so that's where we start today. So let us use a notation which is closer to Jackson's. Okay, so let us have a for today. Let's use some notation similar to Jackson. So just to make the equations look smaller. Okay, so chapter 14 in my book. So that simplification is that instead of writing source and the field point all the time by giving R and R prime, you basically say that the field point, so the source has something like this. So I'll define something like this, R, vector R. And T prime basically means always, so over here, if you look over here, prime is always the source and unprimed is the field. Okay. So T prime is the source. Small r prime, and this r prime is basically an r prime is a function of T prime. Okay. And r of t is just r of T prime. Also, we'll define the direction by taking an end gap, which is this by this. And then in this notation, we can write down the fields, the linear widget fields for a point particle. So then we have the linear Richet fields for an accelerating point charge. And that can be written, so the notation which is short form is basically can be written as Q by some kappa times R. I'm going to define it in a moment. Okay. Got it. And A is equal to, again, Q U C kappa times R. So the whole point is that this square bracket with that retarded basically means, so basically where by my definition anything like this x, okay, within square bracket and retarded, it basically means that it has to be evaluated at the retarded time, okay, and so this is x at r prime and t minus r minus r prime by c. And kappa is defined as basically an angle. So kappa is equal to 1 minus n cap dot u by c. Or we can think of u by c as beta. So 1 minus n cap dot beta. So this is the notation in which most of this Jackson or other books are written. So we'll go to this. Okay, so then a couple of points over here. So once we do this and write it like this, you'll notice that this potential over here, this potential due to a moving charge, accelerating charge, is different from a static EM potential. That's of course. So the potential due to moving charge is different from static potential. And this difference can be attributed to two things. Okay. The first is this kappa. So look at this kappa. So one is basically the factor kappa. Okay. So this kappa, if you look at the formula, becomes important. This factor becomes important when you go to high velocities. So important at high velocities. Okay. So when you go to high velocities, because then u by c, that becomes very closer to 1. So this thing becomes very closer to 0. That tells you that at high velocities, these potentials are concentrated in a narrow region around the direction of the velocity. So potentials are concentrated in a narrow region along direction of velocity, so along direction of motion of the particle. Okay. So this is like the beaming effect, and this is actually related to the beaming effect of which you have found in the special theory. So this is beaming effect. So that one thing, that's something different. The other thing which is different, I don't know how I'm getting so thirsty today. So the other thing that is different, of course, is that it is calculated at the retarded time. And that makes a big difference in the answer. So everything is calculated at the retarded time. Because it is calculated at the retarded time, this makes the particle, it makes the particle possible to radiate. So let me explain it what I mean. This makes radiation from the particle possible. Now, when I talk about radiation, it means that there has to be some energy flow that goes from the source and goes far away, right? That is radiation. So energy is carried out. You have known about wave packets and how the energy and momentum are carried out the wave packets. So it must go away and it must go very far away. Now, typically, the potential falls as 1 by r, right? So in general, for example, for the static case, in general, potentials falls as 1 by r. So if I want to differentiate this potential to give the field, so fields falls as 1 by r squared, right? So basically means that if I have a static potential, then it will fall as 1 by r squared. So your fields will die down very fast. It will not go far away. However, if you look at the equation for the E and B, I'll write it down soon, you will see this differentiation with respect to this 1 by r factor at this retarded time gives you an extra 1 by r factor. So over here, due to the retarded time, we have an extra 1 by r factor. So there is a 1 by r squared factor. But because things are evaluated at a retarded time, you will see there is a 1 by r dependence. Now, when there is a 1 by r dependence, it basically means that you have something that goes too far because it does not fall off fast. So your effect is felt at very far away. And so as you go to larger and larger distances, 1 by r dominates. So at far distances, 1 by r dominates. This basically means there is radiation propagating at far distance. So this is a very important point, that in general, your fields fall as 1 by r squared, but when you have radiation, at that time, the fields do not fall as 1 by r squared, it falls as 1 by r. And that's why you have radiation. That's why you have things which can, your effect can be felt at far away places. Now, this.
So you mean extra r factor, right? Not 1 by r.
There's a 1 by r. So there's a 1 by r squared and there's a 1 by r.
So totally it's 1 by r cube.
No. There are two. In a moment, I will show you. There are two parts to it. There's a 1 by r part and there's a 1 by r.
Oh, okay, sum of terms. Okay.
Now, yeah. So these two are very important 2 points. As you can see, just because you have moving charges, there are 2 things have come. One is the fact that there is a 1 by r factor dominating the potential at large distances, and the fact that if you have high velocities, then your fluxes are in a cone along the velocities. So what we want is that we want to now write down the E and B field. Okay. So we want to write down the E and B fields. So we want E and B fields. Okay. So we need the R at this retarded time and T retarded. Okay. So the particle has velocity u, which is basically R dot at T retarded, and acceleration, which is dot double dot. So this is what we want. So let me sort of draw a schematic to basically tell you what looking at. So you have a trajectory. So let me draw some trajectory. Okay. And let's say this is the present position of the particle. So this is present position. Okay. And this is at time t. Time t. And this is somewhere which is the field where I want to find what is the E and B or what is the potentials. This is R. Okay. This is also at time t. But this field position is affected by when the particle was at a past, so was at some previous position. So let's say it was over here. Okay. So over here, the particle velocity was something like this because it was going in this direction. Okay. So this direction is the beta. Okay. And so this is position at time t retarded. This is basically the path. This is n direction. Gap. And this is basically beta dot. Okay. The acceleration. If the particle was relativistic, the acceleration, the four acceleration, and the four velocities, they are perpendicular to each other. So this is what it is. So over here, just to remind, your beta is basically u by c, and your kappa is 1 minus n cap beta. Now, if you go to Jackson and find out what is your electric and the magnetic field at this position, okay, R, remember, is R minus R prime. Okay, that's what R is. So then I'll write down the equation from the electric and the magnetic field. This is a slightly just laborious calculation, but it's also there in Griffiths, so you can look it up. So your E field over here, the E is your field. So one problem over here, sometimes here is field, sometimes E is energy, but I don't know what to do about it. So it's a single charge which is moving. So this is a charge Q which is moving. Okay. So then this will be Q times is the first term, which is n cap minus beta into 1 minus beta squared divided by kappa cubed r squared. And when I do this box, remember it basically means it is evaluated at a retarded time plus q by c n cap by kappa cubed r, and then this is multiplied by n cap minus beta cross beta dot. And your magnetic field is just, you know already that magnetic field and electric field are perpendicular to each other. And so your magnetic field at RT and is also perpendicular to the direction. So this is basically again n cap plus E. Okay. Similarly, if you have written the electric field, then this would be minus n cap plus E just. So your B is perpendicular to. Now, as you can see over here, so let me, there is an r squared term over here, and there is an r term over here. So when you go to far away distances, obviously the first term dies down, the second term starts dominating. At some point, of course, it has been multiplied by some other factors, and that factors will tell you at what distances one will dominate from the other. But obviously, as you go farther and farther away, your second term will start dominating. Okay. So if you look at the E field now, okay, so the first term in the E field, look at the E field. The first term, okay, this is basically the velocity field induced term. So over here is a velocity is there. There's no acceleration over here. The first term is the velocity field induced term. Or I can call it, let's say, some P velocity in some sense. And this is proportional to 1 by r squared. When your velocity is very, very small, so look over here, when u is much, much less than c, then this is just like a Coulomb's law. Then this is just Coulomb's law. So the first term is just a generalization of the Coulomb law. So instead of a charge being static, a charge is moving at some constant velocity. That's the only difference. So it gives exactly something which is you have seen in Coulomb's law, which is the 1 by r squared. As I won't say a homework, but something that you should think about. So this is like a homework, but I'm not going to find out from this figure, and by looking at this equation and try to deduce or argue what is the direction of the velocity induced. So what is the direction of this? That's an interesting answer. So we may want to think about this. Okay. Then there is the second term over here. So in the second term, this is acceleration induced. used, okay? And this is proportional to 1 by r. This is the radiation field. Okay. So if I just look at the radiation field, you have the E radiation, which is R and T, which is Q by C. Cap by R multiplied by n cap minus beta plus acceleration. And you have a that both the cases evaluated at the retarded time. And the last thing is that you're also, if you look at the actual value of the ERAD, it's a magnitude of the ERAD, you know this already. Your BRAD, let's see here. Right. Okay. So this is what your radiation field due to a one single moving charge looks like. This is one single moving charge, just one charge. So what we have found, again, a couple of things. One is that it goes as 1 by r. The second thing is not like the over here or in the static case, your direction of your E was basically not perpendicular to the n cap, but for the radiation field, your E is perpendicular to the n cap, and B is just a consequence of that. For static case, E is not perpendicular. So if I have one charge, E is not perpendicular. Now the whole point is there some way of understanding what's happening? I mean, of course, the equations, the calculations tells you the answers, but can we have a heuristic understanding of why the radiation field has this different nature, and very different nature, which makes it so important, than a non-radiation field. So an accelerated charge induced potentials and other things is different than a non-accelerated or a static charge. So why is that? Okay. So let me try to give a very heuristic kind of not explanation, maybe some way of looking at it. Okay. So let me try to draw something. So it's a complicated kind of drawing. It may become a bit messy, but let me see how good I can do it. So to begin with, instead of having this curvy trajectory, let us think of charge going in a straight line. One charge moving in a straight line, a constant velocity. Okay. So the charge is moving in a straight line. Okay. Okay. And so it's an x. Okay. And the charge q, and moving with some velocity, some constant velocity. So it's a constant velocity. Now I can label my time coordinates, and the way I want to look at acceleration is to make it a sudden thing instead of a gradual acceleration. So this charge moves at a constant velocity, okay? And let's say at t equal to 0, it is at x equal to 0. And over here, it suddenly stops. Okay. So there's a break in the velocity. It suddenly stops at x equal to 0. So let me sort of keep on writing what I want. So your q, okay, is traveling along x, okay, constant velocity, stops at x equal to 0 at t equal to 0. Now I go to the next time step, okay. Let me call it t equal to 1. So let me call this something over here. Maybe, okay, over here. Let me call this t equal to 1, x equal to 1. So next time step t equal to 1, which defines the speed of light. Okay, so basically I say if I have this x equal to 1 is basically c into this distance, into this time interval. Okay, so at t equal to 1, at t equal to 1, next time step, okay, we define some radius. So this radius is basically this x0 to x1. Define a radius that is x0 to x equal to 1, okay, which is the speed of light c. Okay. Okay. So now let me define this radius. So let me now draw something with this radius. So this is, okay. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right. Now inside this radius, so which is this green line that I said, maybe I should have gone with the green dotted line, doesn't matter. Inside this radius, so inside this green radius, the field lines are pointing at x equal to 0 because it came and stopped over here. The field lines are pointing at x equal to 0 because the charge came, stopped at x equal to 0. The field lines will be pointing at x equal to 0. So let me draw the field lines over here. Let's say like this. So inside the radius, the field lines are pointing at x equal to 0. I hope you guys are with me till now. Remember, this radius is c, Okay, so this radius is basically C. Outside this radius, no info has propagated that this charge has come and stopped at x equal to 0. So outside the radius, no info has propagated that charge has stopped at x equal to 0. Okay, so there's no knowledge of the charge stopping. So outside the radius, people think the charge is moving, or whatever people are, whatever think the charge is moving. So the field lines outside the radius are pointing, because this is at the next time step, okay, at x equal to 1, because it has no idea that the charge has stopped at x equal to 0. So it field lines points at x equal to 1. So outside the radius, if I look at the field lines, then the field lines will point at x equal to 1. So let me try to draw the field lines a bit better. These are the field lines outside the radius. So the field lines over here lines point at x equal to 1, because no information has gone outside the radius of C. Right? Now, this, if you look at this figure, what is inside the green line is true. What is outside the green line is also true. Okay. But there cannot be any discontinuity over here. If I have to have a flux conservation, if you have to have Gauss's law, then there has to be a consistency between these two regions. Okay, so there has to be a connected part. Gauss law, okay, and flux conservation implies there has to be a connected part, okay, slash continuity. So these are radial feed lines. The only way this can be connected if there is a transverse feed lines over here. Okay, so the only way these two can be there if there is a transverse field, not only this radial field, but there is a transverse field at this small region. Let's say instead of a line, let's say a small annular region where this line is. So there has to be a transverse field over here. Right. So this means there has to be a transverse field at r equal to C at this distance. Right. Now, because there's a conservation of fluxes, okay, there's a conservation of flux lines due to conservation of flux lines, one can show or one can argue that this transverse field, so there is, see there over here along this green circle, there is a bunching of lines. Okay. Now, due to this conservation of flux lines, this transverse field has to go as 1 by r. Why? If you take an annular ring, let's say you can take an annular ring over here. Okay. Now, this annular ring is of the same thickness. The annular ring of the same thickness, because the thickness is basically the light travel time into the acceleration time. So let me try to argue. Just think. Transverse field. So you take, let's say, argue like this. You take an annular ring, okay, which is perpendicular to the line of travel, which is perpendicular to line of travel, containing all the flux lines. The annular ring is the ring where all the flux line from radial becomes like this and then goes away, which contains all the transverse flux lines. Okay. Now, thickness of the ring is basically a constant. Why? Because this is nothing but the light travel distance. So this is nothing but the light travel distance into acceleration time. Okay. So instead of x equal to 1, they can do x equal to 2. Wherever the thickness will still be the same. Now, the radius of the ring is proportional to r. The ring is proportional to r. Now, since flux lines are conserved, this means the strength has to be just 1 by r, because total density of total number of flux lines has to be the same. So this very heuristic, this heuristic kind of argument.
Sir.
Yes.
The strength is where? Inside the ring?
Say again.
This strength is inside the ring, right? Inside the annular ring.
I can't. What spent?
I'm saying that the strength which you told about, that strength will go like 1 over r. It is inside the ring, right?
So think of an annular ring. Your flux. So this is, there is a bunching. So I don't want to spoil this figure, but I will, so there's a bunching over here, right?
Yeah, yeah.
Right. Now, if you think of a larger ring over here, think of a ring at a twice the distance as. Okay. The thickness is still depends on basically how fast it goes and stops.
Yeah, I get you.
So thickness is still the same.
Yes.
But because at a farther distance, because thickness is same, the total region, area of the ring is large.
Yeah.
So your density, the flux density should be basically, because the area has gone up by this r times the thickness, your flux density has to go by 1 by r times because the flux is conserved. So because the flux is conserved, you see this E, which is whatever this field, which was transverse to the line of sight, that is not only transverse, that goes as 1 by r. And that heuristically is because.
But sir, if it is transverse, then it will not give any flux, right?
No, it will, no? I mean,
If it is parallel to the surface, how can it give the flux?
no, over here, transverse means whatever I'm drawn over here. The blue lines that is I have drawn away, this is the transverse.
Yeah, it's parallel to the surface, right? At each point.
Parallel to the circle, yeah.
So if it's parallel to the surface, then the flux will be 0.
No, you look at the density of lines over here and the density of lines over there. So think of the density in a smaller circle, the radial number of lines in a smaller circle, how many you can connect over there, and take to bigger circle and think of the radial numbers. You'll see that the densities will be such that the number of lines is still the same, right? Because it's the same number of lines that goes there, goes here. So think of it like this. I mean, this is not a very good way of thinking, but think of it like this. Let's say I take some other.
So I got what you are saying, that is fine, but I'm not
Yeah.
talking about that. I'm saying that we have to first find the flux, right? Flux is simply E dot ds.
Yes.
And if you take the flux at this sphere, then it will be 0 from this. This is the transferred part, right? Transferred part will have the 0 flux.
See, the total flux is conserved. You have the
Yeah,
total flux is conserved. So the E dot ds is some number.
Yeah, that is fine. But the point is that if we look at this diagram, we can see that at each point, the field is transverse at the sphere of the radius of the sphere at each point. So it's like that there is
No,
no
no,
flux
no,
going outside.
Nikhil, you're doing a vector addition. I'm not doing a vector addition over here.
Sir, I'm not doing a vector addition. I'm just saying that
It's just
there
the
is-
density. The same density, think of this light, this blue color, the same density goes over here, goes over here, goes over here. Then the flux is going down at every step, right? Unit area, the flux per unit area is going down because the area is increasing.
We are talking about flux from which surface?
Let's say a flux that goes from this to the, so this is the same, this flux is the same as this flux which is in this region there, over here. Because your flux lines are connected, right? Think of it like this. Flux lines are connected. So whatever is going like this, you can think of this getting connected and going like this. The number of flux lines, but over here, it has to go down less because the annular area, annular volume is more on over here than over here. So flux conservation tells you that your density has to go down and your amplitude is the density.
Okay.
This is always the case. Anytime you do any flux conservation, for example, I don't know, let's say you have classic, there are very classic examples in plasma physics or in astrophysics. No, you have magnetic fields, which suddenly you make it into a smaller region, then your amplitude will go up. This is conserved. But if you think of this magnetic fields as just lines, right? You can think over here also as lines, which goes radial, then becomes transverse, then goes radial, then becomes transverse, goes radial, then becomes transverse. Now, obviously, in a propagating case, what is happening is that these transverse regions are just one after the other, right? What we are doing is a very heuristic, arbitrary way of saying that why it happens for a delta function kind of stuff. Stop it. But every time it becomes transverse, when it goes to the next transverse layer over there, because the flux strength has to be the same, area is density times the volume. The density is your E, because that's what you measure, right? In a sense. Because you always measure when you do E, when you look at, you do it per unit solid angle, per unit area, that's a volume over there. So E is coming down. And the way your volume is increasing, which is basically by 1 by R over here, by R, because this volume is increasing just by the radius. So your density is going down by the radius. When we looked at this energy per unit frequency per unit solid angle, basically the same thing over there also. Okay. So is there a lot of confusion over here? I thought this was a nice way of describing things, which is generally you don't see a very heuristic way of seeing it. Why it should be, and that basically is the exact consequences that within a certain region, basically the consequences of the fact that your information is propagating at some speed. It's not instantaneous. You see, this is the beauty of this. I mean, it's connected to the whole fact that this action at a distance is not there. There is a propagation of information, and the propagation of information actually renders itself to this nature of the radiation field by which it propagates. This is something I don't see in most of the books written down. Anyways, I want to quickly do a couple of more things. I mean, I'm doing it slowly. So once we have this kind of radiation field given by this equations, we can also calculate its spectrum, something that we do all again and again. So we can look at its energy. So we can look at the spectrum. Okay. So look at the energy per unit frequency per solid angle. Okay. So of course we have something where you look at, so, but this is basically not your energy. This is the electric field. Okay. Sometimes it becomes complicated. So over here, whenever I talk about energy, I write down W, not E. So you have some time variable E, and you know that we have written previously that if you look at in the frequency domain, is just a Fourier transform. Okay. So we wrote this. Okay, this is it. And then from here that we've done before, then this gives this energy per unit area and unit frequency. This thing, we saw that this was basically equal to this cross spectrum thing. I hope you remember this. I mean, we did this like 2 or 3 classes before. This is something that we found, that you can write down the energy per unit area per unit frequency, and we get this kind of stuff. So now what we can do is that we can input what is this E omega for this radiation field. Now for the radiation field, we have E of t, and so then we use the radiation field E of t over here, and that will give us your E omega. Okay. So for the radiation field, then what we have we'll have a c by 4 pi squared, because this 2 pi and 2 pi will give you a 4 pi squared. And then we'll have an integral where, so let us write all these things carefully. We'll have an integral, and then we'll have the real part, okay, of p of t over t dt square. The box is because radiation is always at retarded time. Now you substitute this over there. Once you substitute this, you will find that this becomes your q squared by 4 pi squared c, and then this expression, which was integral n cross minus beta cross acceleration kappa cubed for pi omega t, and then square. So expression in the bracket is again you have to do it in the retarded time. Okay, the expression bracket means retarded. Okay, so your t is basically your t prime is equal to t minus r of t prime by c. You change your variables to t prime, so you change variable to t prime. Okay, then you get your dt is equal to kappa times dt prime, and then you make one more approximation. So you want to look at a field which is far away. So you take the approximation of far away field. Okay. What does far away field means? It means that your R, the field point, that must be much larger than the particle trajectory. So this is R0 was the particle trajectory, remember. So R0 is a local particle trajectory and looking at some field point which is very far away. You take this approximation. Okay. In this approximation, then your R, remember, was your big R, capital R was, remember, was R minus R0, right? So then you can, with this kind of approximation, you can write your R t prime, okay, this thing, we can write as R minus n cap dot. So now again you feed this back into this equation. If you feed this back into this equation, remember, then your t prime over here, this t, remember, will be in retarded time, and that has an R and R cap. So all these things will go in, right? So then what we'll have, you feed back, then, so again another then, you will get this energy per unit solid angle plus unit area is equal to q squared over 4 pi squared c. It's a big expression, I'm sorry about that, but then we have an integral, then an integral of n cap cross n cap minus beta cross beta dot, this thing, okay, over kappa one kappa goes over here, so it's kappa squared, then exponential of I omega. So now this square bracket no more means retarded time because already putting in the retarded time. I omega t prime minus n cap dot r0 t prime plus c t prime and this whole thing squared. I think I've written this equation very badly. Hopefully you can understand this equation. Let me write it down a little better. Okay, now there's one more horrendous calculation where you have to integrate this by parts. Okay, so to integrate this, well, not that horrendous, but it's bad calculation. Okay, so you have to integrate this above equation by parts. Okay, so take first part and then the exponential, the second part, you integrate by parts. And when you integrate by parts, also use this equality. Use n cap, so this n cap cross n cap minus beta dot beta 1. This thing can be written very interestingly as like this: n cap cross n cap minus beta cross beta dot. This can be written as ddt prime of over kappa square. Sorry. And by kappa n cap cross so this equality comes in. Okay, so you can verify that this comes in. So then what you get is this. So one last big expression is energy per unit solid angle per frequency. So you get q squared and omega squared comes over here. Okay, 4 pi squared c, and then this whole thing becomes as an integral n cap cross n cap cross beta. Okay, and then exponential of this I omega t prime minus n cap dot r0 by c. Right. So this really big expression comes, and then what? So now over here, we can do a couple of things. First, before we calculate this for integrate out this part, we can first make few observations. One thing that we can basically do is that we want to do this for non-relativistic particles. So we want to calculate all this right now for non-relativistic particles. Relativistic particles we will do later. So for non-relativistic particles, your beta, of course, is less than 1. Okay, and then if you look at the velocity dependent part and the radiation dependent part, we can make a couple of comments before we actually go and do this thing. Okay. So let me try to see what I wanted to say over here. So first thing I want to say is, so non-resistive particles will simplify this quite a bit. Okay, we'll see that. So over here, if I take the ratio of the two terms that went into this electric field for radiation, the accelerating part and the non-accelerating part, this is R u dot by c squared. Okay. And over here, if you focus on a single Fourier frequency, let's say I focus on one single frequency nu. Okay, let's say this is the frequency of, or a frequency of, oscillation, or say a frequency of oscillation. So if a charge is going in a circle, then it has a frequency. It's accelerating, so it will radiate. Okay, frequency oscillation mu. Then over there, of course, your u dot by u, this is roughly equal to nu. You can check that. Then your Erad, radiation, the accelerating part versus the velocity part, this becomes R u dot by u is, so R u nu by c squared. So I can write down as u by c and R by lambda. So this tells us, over here we talked about this far away zone and nearby zone, right? Far away zone. So over here we can now define how we actually say something which is far away zone. So over here there is one which I will call the near zone. Okay. So where R is less than or equal to lambda. And over here your velocity field is more. Okay. So if there is some frequency of an oscillation or something which gives you some length scales over which you are moving, over here it's very simple. Going in a circle, then circle is the length scale. So anything which is nearby is, that's region of the circle that gives it. Or if you have a far field, and far field will be given by R, which is greater than lambda, but modulated by this C by U. Okay. So over here, your radiation field is more. So these are the two regions that one can look at. And so now if I go to my original equation over here, okay, this original equation, and look at this non-relativistic case. So when beta is less than 1, you'll find that my E radiation, okay, is equal to, again in the retarded time, Q by RC squared n cap becomes a very simple formula for this. And your B radiation is just okay. If you calculate the magnitude, so now I can calculate the magnitude by actually taking into account, we have a figure, you can look at that figure and calculate some angle and calculate the magnitude over here. Over here, you look at this figure, you provide an angle between n cap and beta as your angle theta. So you calculate the magnitude over here, the magnitude. So for the non-relativistic case, you get a simple formula where your magnitude of irradiation becomes the magnitude of irradiation, and that is again Q U dot by RC squared sine theta. So these are the two things that we find for the non-relativistic case. Okay. Now, so just from over here, this theta is basically the angle between U and N. So if you think of your N like this, you know, N cap like this, and over here somewhere you have a velocity of the particle, which is, you know, the acceleration is like this U dot. So this is the theta. And on N cap, remember, if there will be an irradiation. Okay. And your B will be into the plane of the paper. So your N cap and U dot is the plane of the paper. B goes into the plane of the paper, irradiation. So this is the cap. Now, given this E and B in the simplest form where the velocities are completely non-relativistic, I can calculate the Poynting vector. Okay. So I can calculate the Poynting vector over here. And we're coming to one very important result. The Poynting vector. The Poynting vector is C by 4 pi E rad squared. Okay. And so this is equal to the multiply the C by 4 pi. Okay. Q squared, U dot squared, R squared, C4 sine squared theta. Once I know the Poynting vector, I can calculate what is the energy per unit time per solid angle. So now, given this Poynting vector, I can calculate my energy per unit time per solid angle. So this d omega. So this is how much energy is taken away by the Poynting vector. So you need to know the Poynting vector, you multiply by the area for the solid angle. Right? So take this up to the Poynting vector. Poynting. Okay, so this is in R per second per centimeter squared, and multiplied by dA, which is basically R squared d omega. So that's the area. And so this will give you this number. So you have your Q squared, U dot squared, 4 pi C cube sine squared theta. Now, once we have come to this, we can do the final thing over here. I can integrate over all the solid angles. Okay. So if I integrate now for the total power, so if I want to calculate the total power over all solid angle, okay, then my total power, okay, this is dW dt. So energy per unit time, which is the total power. I have to integrate over all the solid angles. And so this becomes your Q squared U dot squared by 4 pi C cubed. Okay. And then sine squared theta. So remember. And this can be easily done. You can do this. This you'll see comes out to gives you a 8 actually. So this will become 2q squared u dot squared over 3c. Okay. So this is a very important formula. This is known as the Larmor formula. It tells you how much, for a non-relativistic charged particle, how much energy it radiates per unit time. So if I want to calculate something like how quickly the charged particle will cool, how far the charged particle will move, because it is radiating, this is what we're going to use all the time. If you can calculate this, this is the simplest formula, one particle, non-relativistic, and you see it's a very simple closed form equation. You get the total energy per unit time, the total power radiated by a charged particle. One of the very classiest formula that's in physics, called the Larmor formula. Couple of things you can quickly say about the Larmor's formula. First is it's proportional to, so first your P is proportional to the charge squared. It is also proportional to the velocity, acceleration squared. Okay, so here's the acceleration. U dot is an acceleration. So it's proportional to both the square of the charge, the square of the acceleration. So you change things a little bit, your energy radiated becomes very fast. Number two, if I didn't integrate over the angle, this is number 1 point. If I didn't integrate over the angle, then the energy pattern, energy angular pattern, is basically sine squared theta. Okay, that's the angular pattern of the energy. So basically, it has a dipole pattern. So this is a dipole pattern. Okay, so there is no radiation along the acceleration direction, and is maximum perpendicular to the acceleration direction. So there is no radiation along acceleration, maximum radiation perpendicular to acceleration. Okay. This is the two classic things for Larmor formula. This beautiful dipole pattern like this. Okay. This beautiful dipole pattern. Now, once it becomes very, very relativistic, this dipole pattern will be very much skewed on one side. Okay. That will happen. There's of course polarization. One important thing is that this is only for non-relativistic particles. For relativistic particles, it is going to be very, very different. Okay, so at least we have gone on and found what is the power radiated by a simple non-relativistic particle. One particle is never the case. Most of the time there will be a bunch of particles. So next day we'll start from over here and calculate what happens if there are n number of particles, not one single particle. Okay, they're all non-relativistic to start with, and then what kind of radiation there will be, whether there will be a dipole pattern or not, what happens. Okay, and then we'll try to generalize it even further, and then we'll see as we go along. So that's all for today, and the next day we'll start with many charges, many velocities, and again we'll try to see things by looking at what are the regions which are more important, what are the regions which are less important in that. Try to break down. Before we do this kind of stuff in a more heuristic, slightly not hand waving but more physical way, then we go into a full detailed blown out calculation. So if you are already intimidated by formulas like this, just wait. You are going to get much more complicated, much more lengthier formula in the very near future. So I will leave you over there. I just hope that you are getting something new and different from what you have done before in your undergrad classes. If that is so, then I will be happy. If that is not, then, well, I don't know. We have to wait. So we'll stop over here.
Sir, what will be the syllabus from the radiation part? No, it's
Typo up to. I mean, the next day, basically, what is there in next day? Little bit of next day. Basically, not the full of next day, part of next day. I hope that I could have finished it today, but I could not. But mainly this non-relativistic radiation.
okay, sir.
Yeah, Anuma, you can stop recording. I think we are done.